Welcome to another video explaining the universe using the particle model. Well, today's video is on the diode, an electronic component used in circuits. So the question might be, what is a diode? If you're not familiar, this is a symbol for a diode. It has a positive end called the anode, highlighted by the triangle, and a cathode they call the negative end. Typical diode would look like this with a stripe, where the stripe identifies the cathode end. And it's a two-terminal component that conducts primarily in one direction. Current can flow this way. It has a low resistance in that direction. That's called a forward bias. And it has a high resistance when current tries to go the other way. It doesn't flow very well at all, and it's called the reverse bias. An example of a diode being used in a circuit is like in a power supply, and it has a diode bridge, a very interesting circuit that takes AC and converts it to pulsating DC. The positive half of the cycle the current would flow this way. It conducts this way through the load, back through, conducts this way, back to the negative side. At the other half cycle, when this becomes positive, it goes through this diode to plus, and then around and back. So in both cases, in half cycle, the positive ends up on this terminal on this one, and you get a pulsating type voltage waveform. That's one use of the diode. Okay, we're going to talk about the diode structure, and we're going to be talking about a silicon diode with proper doping, and is put together at a point called a p-n junction. This is the junction. The p region is doped typically with boron and gallium, although I'm sure there's lots of different material they use to dope the diode material. And the N region is doped with phosphorus and arsenic. What happens is in the P region, you end up with a material that has missing electrons. And the N region, you have extra electrons. P region is generally thought of as positive, the N region as negative. And what happens when you attach a battery, the plus end of the battery to the plus end of the P region where there is missing electrons, this is plus, that's plus, it pushes the positive ions or particles in this direction, and the negative side repels the electrons and pushes the electrons in that direction, and it creates a very narrow area called the depletion range. And this is a forward bias diode conducting current. Okay, this is what I just explained, but there's also the reverse bias. In this case, the battery is twisted around, and the negative end connected to the P region, positive end to the N region. The negative end attracts the positive particles, and the positive end attracts the negative, and it creates a larger depletion range, making it difficult for any movement. Here, the depletion range is small, and it can, they say, diffuse past these points and flow. Forward bias, negative bias is the general explanation. So why the lesson on diodes? To highlight the difference with the particle model. I mean, then there's two main differences, and others. There are no charged particles in the particle model. And there is no EMF to push electrons. There is no electric field. You might see that on occasion. And yet, the particle model explains the diode. The most interesting part of the diode is its IV curve. I for current, V for voltage is generally called the IV curve. And it has a very unusual wave shape. The first quadrant is where you have a forward biasing. In this straight region right here, they tend to operate the diode in this region when it's forward biased, and operate in this region when it's negatively biased. And this is the current, and this is the voltage. The interesting point is that when you get enough current up to here, the voltage gets to 0.7 and basically never changes. You can apply a lot of current, still 0.7, or nearly so. It does change a little. Or you can come down and it's still 0.7. It's a very unusual curve. And it turns out that both curves are, in a sense, the same, but the diode is not a balanced thing. This is, you have the N region and the P region, and they're different. So we're going to compare this to something that is more normal, if you will, for a resistor. This is the IV curve for a resistor, current, voltage, and it's based on Ohm's law. The current is equal to the voltage divided by resistance. You increase the voltage, you get an increased current. Decrease the voltage, you get a decrease in current, and that's a straight line curve where the slope is basically determined by 1 over R. Particle model has an equation, and then we generate the same. I use volts over resistance. And if you watch some of the previous videos on circuits, you'll have seen where I have shown a current that is proportional to a number of G1 particles entering the diode or entering the resistor. Same straight line curve. Now, that's not the same as the IV curve. Well, you can go to the internet and anywhere you want. There's lots of information about the diode. We have nice pictures. They have voltage waveforms. They have equations. No explanation as to why this curve, the diode, behaves this way. Okay, so we're going to talk a little bit about this to get a proper idea to compare the standard model with the particle model. And I'm going to use this 9-volt battery through a 9K resistor and a diode. Typically, you would expect 1 milliamp to flow. But as I said, there's a 0.7 volt drop across the diode that has to be accounted for. So you need to subtract that voltage from the 9 volts, divide both of them by 9K, because this diode has a low resistance, and you end up with 0.92 milliamps. That's the standard. This is a standard equation. Now, circuit. This is the particle model circuit. In the particle model, we don't have current flow, we have G1 particle flow. And I've designated the number of particles by letters A, B, and C, because they are different. A is what I generally would call the base flow of G1s, and it's determined by some constants that I've been trying to work on. A, uniquely, this is an important point about the particle model and circuits in general. A, in a sense, continues all the way around. It never really changes when the circuit is stable. But the battery, on the other hand, it adds G1s. You have a number coming in, you add them. Well, how many do you add? Well, if I assume that the volts per G1 is 0.1, then you divide 0.1 into 9, you get 90. There are 90 G1s being added by the battery such that B is equal to A plus 90, and that's how many G1s you have coming into the diode. But now we know that from the IV curve that when you get a right amount of current flowing, you have this 7-volt drop. A 7-volt drop means the diode loses 7 G1s, because 7 times 0.1 is 0.7 volts. So the diode is going to lose 7. If the battery adds 90, the diode loses 7. Resistor is going to end up losing 83. It's going to have an 8.3 volt drop. And you divide that by the 9K, you get the 0.92 milliamps. So we're going to follow I'm going to use B as the input to the diode, and I'll talk about a resistor. B represents how many are coming in. Okay, so I'm going to change the value of B. I want to change the number coming in. I want to change it with a low number, meaning low current, a low number, low current, which will be operating rate in this region, then a higher number, higher current. To do that change in a resistor, I'm going to leave the 9 volts alone, and I'm going to decrease the 9K to 4.5K, then down to 2.25K. And I'm going to change the value. I'm going to increase it. It's going to start out low and have more and then more. And so here's the chart showing that. This isn't specifically about the circuit. It's about an individual resistor and an individual diode, and what you might expect to happen by using the IV curves. So let's start out with 9K resistor, get 1,000 ohms, 1,000 G1s. And this is just an arbitrary, both are arbitrary numbers. I'm just giving an example that, let's say, for example, the number lost by going through the resistor is 10. Well, when I decrease the 9K to 4.5K, I double the number. I now have 2,000 G1s entering the resistor, and you would expect, because it's a straight line curve, to be 20. When I reduce it again to 2.25K resistor, 4,000 enter the resistor, and you get 40. That's the straight line function. You do the same thing for the diode. That's not what happens. No matter what, you lose 7. You would expect that when it doubles, you would lose 14. Or when you doubled it again, you would lose 28. But you only lose 7. That's what the curve tells us. The question is, this is the question, how does a diode keep the G1s from hitting when the value of B increases? You increase B, 7 of these don't hit and scatter. You don't lose them. Half of them get through. Here, a lot of them get through. 21 of them get through without hitting. So what causes that? When you answer that question, you've answered the question you've explained the IV curve. So here is the particle model for the diode. The diode is surrounded, as I've said in many, many times, every component, every circuit, the earth, my body, all surrounded by a G2 particle field. And I always assume, for simplicity, that all the number of particles entering in all sides in 3 dimensions is equal. The number here and the number here are equal, and this is the one of most interest. Now, this is the P region where you have missing G1s, because it's positive, and so it's missing electrons. The N region, you have extra electrons, and that goes from here to the junction. This is the PN junction. Well, the force at this point and the force at this point are the same, because these particles, as they pass all the way through, are going to lose a certain amount and have a net force here, these go all the way through, going to lose the same amount nominally, and you're going to have the same net force here, and it's at its strongest point. The force gets weaker and weaker and weaker until it gets to the junction. Well, it doesn't lose as many in this part. Excuse me, say it. Yes, it does not lose as many. Got to say that right. It loses more in this part because G1s interact very well with the G1 particle. So this loses a lot. So this force is smaller, and this loses not as much, and then, so this force or number of G1 particles is larger. You have a net force in this direction. In fact, you have a net force all the way down towards, you get to this point where I'm suggesting that there's a point in the N region where you have equal and opposite G1 particles and hence no net force. So you have a force that's constant, that's strong here, strong, it gets weaker and weaker and weaker and weaker until it gets equal. Same ratio, only it only doesn't take as long. That's the operation, and we're going to explain this curve using that. And we're going to explain it. Here is the explanation. The asteroid, I'm going to give you an analogy. An asteroid, consider an asteroid moving slowly by the Earth and too close. It will be attracted by the Earth and hit. But if its speed is slightly higher, even a little bit higher, even when it's close, it will pass right by and not hit. I'm going to I set up the idea that the speed of the G1 particles has an effect on whether the particles hit or not. A G1 particle with a high speed will pass through a component more easily. It will not hit, and it will hence not scatter. Now, this speed, idea of a speed as it enters a component and leaves a component, it's true for the diode, it's true for the resistor, and it's true for the electromagnet. In fact, if you watch this video, we'll go through a very detailed explanation of forces and the vector components of the force, showing how the particle, G1 particle, as it enters a magnet, speeds up, and then halfway through it starts slowing down. So this is a basic function that happens, the speed. And what it means is the faster the asteroid goes through, the less likely it's to hit anything. The faster the G1 particle, the less likely. There's a second effect. When the number of G1s double, like when I change the resistor from 9K to 4.5K, the number of G1s double, the value of B doubles, and hence the force, G2 force, the G2 gravity on the diode doubles. The increased force causes an increase in the acceleration because that's the force causing it to accelerate in the first place. So when you double that, you cause it to go faster. And you hence increase the G1 velocity inside the diode. So speed is enhanced by the fact that G2 gravity increases. And this is basically the kind of the same chart I just had before, where we start with a nominal number of G1s flowing into the diode. It sets up a force that causes it to speed up to some value, and it loses 7. When you cut the resistor to 4.5K, you will double the force. You will cause an increase, and I'm not sure it doubles. I don't have that. I know the current value doubles, the number of G1s doubles, the force doubles, but you're already moving at speed c and entering it, and the G2 gravity is going to increase it incrementally some, but relatively that incremental increase, it will be a doubling. the actual value, I really don't know. But because of that speed, 7 are not of the 14 that would have hit, don't. And you have 7 coming out. And you have the same thing when you go to 2.25K resistor, 4,000 G1s entering, the force is quadrupled. The incremental change of velocity is increased by 4. Oh, my math is wrong. That's supposed to say 21, and you get 7. What keeps a diode from losing more when the value of B increases? Speed does. And this explains the IV curve. It also gives the first clue that I've had that the IF, the interaction factor that I treat as a constant, isn't a constant, precisely a constant. It would appear it can be affected by velocity. And that my equations haven't taken that into account. And now that I know that, to me it's more like a second order effect, but it's still there. Here's the reverse bias. In a reverse bias, there's no significant movement of these because the battery is turned around, attracting the electrons this way, attracting the positive electrons or particles this way, creating a depletion region. And the standard model says, no, it can't jump that gap. And what we're talking about in reverse bias is operating in this region. We don't operate reverse in this region, although Zener diodes operate out here, but a normal signal diode operates here. So we're trying to explain this, and you'll see there's a slight drop. It isn't 0, but there's a slight drop. So here's the particle model, reverse bias. Same drawing, only this time the G1s are coming in the other way. Not applying a different voltage than before. I'm applying, you'd have to turn the battery around, and in the particle model causes the G1s to come into the P region. Got the same force field. You got a force that's strong here and gets weaker and weaker until it gets to this point and this point. It's equal. Got the same thing. You got a strong force here, and then it's equal here. So what happens as the G1s enter this P type, the G2 gravity, strong gravity, speeds them up so they easily, I mean, this is missing. This has got a lot of space, goes through there easily in the first place, and it's going at a velocity c in this direction. It's going to speed up and get pushed by the G2 force until it gets here, then it's going to slow down. It's going to pass through here easily. It's going to get some resistance here and probably would lose 1 or 2 G1s as it goes through here. G2 gravity at the junction keeps them from going. If all G1s pass through, if all G1s pass through this, there is 0 voltage drop. That's kind of counterintuitive. When we think of current flow, a lot of current flow, you get a big voltage drop. But in a particle model, when you have B entering and B leaving, and you haven't lost any particles, that's no voltage drop. And so that's what happens in reverse bias. That's what keeps it at ground level in this operating range right here. Much simpler to explain because it's being pushed by gravity and to speed up and make it through and not have any significant hitting and scattering. Well, conclusion. I'm always worried when I have to invoke a new feature or a new effect of a known feature. I've known the speed changes. This is the first time I've used speed to explain a characteristic of anything. And so using the speed for the diode, the forward bias, that speed increase explains the nearly constant voltage drop when you operate it in that region. And in the reverse bias, G1s flow easily through the diode being pushed by the internal G2 force, losing none or a few particles. My name is Bob D. Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.